Hello, and welcome to a quiet journey through the cosmos. Before we begin, make sure to subscribe and turn on notifications, so you can join us on every gentle exploration of space and science. Tonight, we'll uncover a simple but fascinating question. Why almost every planet spins in the same direction? Picture the planets moving silently, each orbit reflecting the story of its formation, all guided by the same universal laws of physics. Stay with me as we follow the science, letting your mind settle into the calm, orderly motion of our solar system and the universe beyond. You settle into a quiet awareness of the sky above you, where motion is slow, steady, and deeply consistent. Night after night, the planets rise and set in familiar ways, tracing paths that repeat with dependable rhythm. Long before telescopes, people noticed that these wandering lights move differently from the stars, yet even in their wandering there is order. Over time, careful watching reveals something subtle but striking. Most of these worlds travel around the sun in the same direction, and they also spin in that same general sense. You are not imagining this pattern. It is measured, recorded, and confirmed. When astronomers speak of direction, they define it clearly. Viewed from above the sun's north pole, nearly all planets orbit counterclockwise. Their rotation, the turning of each planet around its own axis, also follows this direction for most worlds. This shared behavior stands out because nature allows many possibilities, yet here there is alignment. You begin with the idea of rotation. A planet rotates when it spins around an internal axis, an imaginary line running through its center. Earth completes one rotation roughly every 24 hours, a fact measured by repeating cycles of daylight and darkness. This spin is not guessed at. It is observed through star positions, satellite tracking, and the motion of surface features. Other planets reveal their rotation through cloud patterns, magnetic fields, and subtle changes in reflected light. Revolution is different but related. A planet revolves when it travels along its path around the sun. This motion defines the length of a year. By tracking a planet's position against distant stars, astronomers map its orbit with high precision. These orbits form gentle, flattened loops rather than random paths through space. When you place all these orbits together, they lie close to a single plane, like grooves worn into a disk. This shared plane and shared direction are not assumptions. They are outcomes of repeated measurement. Telescopes refine them, spacecraft confirm them, mathematical models describe them. Over centuries, the data grows stronger, not weaker. The planets are not scattered in motion. They follow a collective flow. You may imagine early observers standing beneath the open sky, noticing that Mars sometimes drifts backward for a time, a motion later called retrograde. Even this strange behavior fits within the same orderly framework once the full geometry of planetary motion becomes clear. What appears irregular at first resolves into predictable movement when viewed from the right perspective. As instruments improve, the picture sharpens. The invention of the telescope allows surface markings on Mars to be followed across nights, revealing its rotation. Jupiter's bands move steadily, showing a rapid spin. Saturn's shape bulges slightly at the equator, a physical sign of rotation confirmed by physics. Each observation adds another piece to the same quiet message. Spin is common, direction is shared. You learn that motion in space does not require continuous pushing. Once set in motion, an object keeps moving unless acted on by a force. This principle, later formalized as inertia, helps explain why planets continue along their paths. But inertia alone does not explain why the directions match. That question lingers gently, waiting. The sun itself participates in this pattern. It rotates in the same general direction as the planet's orbit. Sunspots drift across its surface in measurable ways, allowing astronomers to determine its spin. This connection between the central star and its planets suggests a shared history rather than independent chance. You notice that exceptions exist, but they are rare. Most of the time, the rule holds. Mercury spins slowly but still follows the shared direction. Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all orbit the sun in alignment. Their differences lie in speed, tilt, and detail, not in the overall sense of motion. The calm strength of this pattern lies in its scale. It spans millions to billions of kilometers. It persists over billions of years. It appears not only here, but in other planetary systems now being observed around distant stars. The same flattened disks and shared orbital directions emerge again and again in young stellar systems. You begin to see that this order does not require intention or guidance. It arises from physical laws acting on matter in motion. Gravity gathers material. Motion shapes structure. Direction is preserved unless something interferes. These ideas rest on experiments, observations, and mathematical descriptions tested repeatedly. As you rest with these facts, the solar system feels less like a collection of separate objects and more like a connected system. Each planet carries a record of early motion, preserved in its spin and path. The consistency you observe today reflects conditions long past, still readable in present motion. This awareness does not rush. It settles slowly, like understanding that arrives without effort. The planets do not hurry, and neither does the explanation. The sky remains calm, not because it is still, but because its movement follows rules that do not change. You are left with a gentle curiosity about where this shared motion begins, and how clouds of gas and dust can give rise to such lasting order, quietly shaping the paths of worlds for ages beyond counting. You remain grounded on Earth as you begin to notice how motion is detected rather than imagined. Spin is not something astronomers assume simply because it seems reasonable. It is something they measure carefully, using repeated observation and comparison. From your position beneath the sky, rotation reveals itself slowly, through patterns that return again and again. For rocky planets with visible surfaces, rotation can be seen directly. Mars offers one of the clearest examples. Dark regions and lighter planes move across its disk over time. By recording their positions night after night, astronomers measure how long Mars takes to complete one full turn. The result is consistent, precise, and repeatable. The planet rotates once roughly every 24 hours and 37 minutes, a fact confirmed long before spacecraft arrived. Mercury presents more difficulty. Its surface is hard to observe from Earth because it stays close to the Sun in the sky. Even so, radar signals sent from Earth bounce off Mercury's surface and return with subtle changes. These changes reveal how fast the planet spins. This method does not rely on vision, only on timing and physics, and it confirms that Mercury rotates slowly but steadily. Venus is hidden beneath thick clouds, making direct surface tracking impossible with ordinary light. Yet its rotation is still measured. Astronomers watch how the cloud tops move across the planet's disk. They also use radar, which passes through clouds and reflects from the solid surface below. These measurements show that Venus rotates in the opposite direction from most planets, a rare but well-established fact supported by multiple techniques. For gas giants, the task changes again. Jupiter and Saturn have no solid surfaces to mark, but their atmospheres display strong patterns. Bands of clouds circle the planets, and storms persist for years. By tracking the movement of these features, astronomers determine rotation rates with high accuracy. Jupiter's rapid spin becomes obvious as its cloud bands sweep around in less than 10 hours. Magnetic fields offer another powerful tool. A rotating planet with an internal magnetic field produces regular signals as charged particles interact with that field. Spacecraft detect these signals as repeating pulses. The timing of these pulses reveals the planet's rotation period. This method is especially useful for worlds where visual tracking is uncertain. You notice that measurement improves when observers leave Earth. Spacecraft orbit planets, fly past them, and sometimes land on them. Cameras record surface features from close range. Instruments track gravity, magnetism, and reflected sunlight. Every pass adds clarity. Rotation becomes a number, not an idea. Earth itself is measured constantly. Satellites track landmarks, oceans, and ice sheets. Atomic clocks compare Earth's spin against precise time standards. Small variations are detected, showing that rotation is steady but not perfectly uniform. These variations are linked to earthquakes, ocean movement, and shifts in the atmosphere, all measured and understood through physics. The direction of rotation is determined just as carefully. Astronomers define a reference point, usually the north side of the solar system's main plane. From this viewpoint, spin direction becomes a clear, measurable choice rather than a matter of perspective. When planets rotate in the same sense, the alignment stands out. Light also plays a role. As a planet spins, light reflected from its surface or clouds shifts slightly in frequency. This effect, known as the Doppler shift, is measurable with sensitive instruments. One side of the planet moves toward the observer while the other moves away. The difference reveals both speed and direction of rotation. These methods are tested repeatedly. Independent teams confirm results using different tools. Errors are examined, corrected, and reduced. Over time, confidence grows. The shared direction of planetary spin is not a belief passed down through tradition. It is a conclusion supported by layers of evidence. You begin to sense how patient this process is. Nothing is rushed. A single night of observation means little by itself. Meaning comes from repetition, from consistency across years and generations. The sky changes slowly, and understanding keeps pace. Different planets require different patience. Some take years to reveal subtle motions. Others announce their spin quickly. All of them respond to the same physical rules, even when the methods differ. The variety of techniques does not weaken the conclusion. It strengthens it. As measurements accumulate, patterns become harder to ignore. Most planets rotate in the same direction they orbit. The Sun shares this direction as well. This alignment is not perfect, but it is strong. Deviations are measured and catalogued, not dismissed. You rest with the idea that observation is an active process. It demands attention, accuracy, and restraint. Scientists do not force the sky to fit expectations. They allow motion to reveal itself through careful listening, through instruments designed to detect what the universe already does. The quiet consistency of these measurements invites a deeper question. When motion aligns so broadly across space, it suggests a shared origin, a beginning where direction is set and preserved, waiting patiently to be understood. You begin by noticing that the planets do not surround the Sun in all directions equally. When their paths are traced carefully across the sky and plotted using mathematics, a clear structure appears. The planets travel along paths that cluster around a single, broad plane. This plane is not imagined or symbolic. It is a measurable geometric feature defined by the average of planetary orbits. From Earth, this plane appears as a narrow band across the sky where the Sun, Moon, and planets are always found. Ancient observers recognized this band and gave it a name that still remains in use. Today, its position is measured precisely using telescopes, satellites, and long-term orbital data. The consistency of these measurements reveals that the planets share a common orbital surface. You learn that this flatness is not perfect, but it is strong. Each planet's orbit is slightly tilted relative to the others. This tilt is called inclination, and it is measured in degrees. Most planets deviate only a few degrees from the central plane. Mercury, the most tilted among the major planets, still remains close compared to a random distribution. These small differences do not erase the larger pattern. When astronomers model the solar system in 3 dimensions, the flatness becomes unmistakable. The planets form a thin disk rather than a scattered cloud. This disk-like arrangement is one of the most important observational facts in planetary science. It tells you that the system has a shared history shaped by rotation and gravity. You reflect on how gravity operates. Matter attracts matter, pulling material inward. But gravity alone does not explain shape. Motion matters. When material collapses while already moving, it tends to spread out into a flattened structure. This effect is observed not only here, but in many astrophysical systems. Rotating stars flatten slightly. Spiral galaxies form thin disks. The same physical principles apply across scales. The solar system's flat shape is measured using planetary positions recorded over centuries. Astronomers calculate orbital planes by tracking where planets appear against distant stars. These stars serve as fixed reference points. Over time, repeated measurements refine the geometry with extraordinary precision. The result is a clear picture of alignment rather than randomness. You notice that moons follow a similar pattern. Many large moons orbit close to their planet's equatorial plane. This is not required by chance, yet it appears repeatedly. The same physics that shapes planetary orbits also shapes smaller systems. Flatness emerges naturally when rotation and gravity act together over time. Inclination becomes a useful concept rather than a complication. By measuring how much an orbit tilts, scientists learn about past interactions. Slight tilts suggest gentle gravitational nudges. Larger tilts point to stronger events, such as close encounters or collisions. The overall flatness remains the baseline from which these variations are understood. You remain aware that flat does not mean motionless. Planets travel immense distances along their paths. Their speeds vary. Their distances from the Sun change slightly. Yet the plane itself remains stable over billions of years. This stability is not enforced by rigidity but by balance. Gravitational forces and momentum maintain the structure without constant correction. Spacecraft confirm this geometry directly. As probes travel from one planet to another, they move largely within the same plane. Mission planners rely on this fact to design efficient trajectories. The success of these missions reinforces the accuracy of orbital models and the reality of the system's flattened shape. You also learn that this structure is not unique. Observations of young stars reveal disks of gas and dust surrounding them. These disks are flat and rotating, just like the early solar system is believed to have been. Telescopes sensitive to infrared and radio wavelengths capture these disks in remarkable detail. They provide a living comparison to the ancient process that shaped the planets you know. The connection between flatness and shared direction becomes clearer. When objects form within a rotating disk, their motion reflects the disk's rotation.
Orbits align.
Spins tend to align. Deviations require explanation, while alignment requires only the persistence of physical law. You rest with the understanding that geometry is not an abstract idea imposed on nature. It is a record of motion preserved in space. The flat shape of the solar system is a visible trace of how matter moved as it gathered, cooled, and settled into lasting paths. As this realization settles gently, the question becomes quieter but deeper. If shape and direction both emerge from early motion, then the origin of that motion holds the key, waiting in the behavior of collapsing clouds long before planets take form. You begin far earlier than the formation of any planet, in regions of space where matter is spread thin and cold. These regions are known as molecular clouds, enormous collections of gas and dust drifting between the stars. They are not theoretical constructs. Telescopes observe them directly, mapping their shapes, temperatures, and motions using radio and infrared light. Within these clouds, gravity slowly gathers material together. You notice something important right away. These clouds are never perfectly motionless. Measurements show that gas within them moves at slightly different speeds and directions. This motion may come from nearby stellar explosions, passing stars, or long-standing turbulence within the cloud itself. Even when the motion is gentle, it matters. When gravity begins to pull the cloud inward, that small initial motion does not disappear. As contraction begins, the cloud shrinks. Its material moves closer to a common center. Here, a well-established physical principle becomes unavoidable. When a rotating system contracts, its rotation rate increases. This principle is called conservation of angular momentum. It is tested in laboratories, observed in weather systems, and confirmed in astrophysical objects across the universe. No special conditions are required for it to apply. You may think of angular momentum as a measure of how much rotational motion a system contains. Once present, it cannot vanish unless something removes it. As the cloud collapses under gravity, its radius decreases. To preserve angular momentum, rotation speeds up. This effect is not dramatic at first, but over time it becomes defining. Astronomers observe this process in real star-forming regions. Using powerful telescopes, they detect rotating disks of gas and dust around young stars. These disks are flattened, not spherical. Their rotation is measured through shifts in light caused by motion toward or away from the observer. One side of the disk moves slightly closer, the other slightly farther. The difference reveals clear, organized rotation. You realize that the sun begins this way. Long before it shines, it forms at the center of such a rotating disk. Material spirals inward, heating as it compresses. The central region becomes dense and hot enough to ignite nuclear fusion. The surrounding disk remains, still rotating, still flattened by motion and gravity working together. Within this disk, conditions vary. Near the center, temperatures rise. Farther out, material remains cooler. Dust grains collide gently, sticking together through electrostatic forces. Over time, these grains grow into larger clumps. None of this requires new physics. Each step follows from observed behavior of matter under gravity. The direction of rotation is inherited directly from the original cloud. There is no opportunity for it to reverse spontaneously. Every collision, every gradual accumulation occurs within the same rotating environment. As material settles into orbits around the forming star, those orbits reflect the disk's shared motion. You notice that this explanation does not rely on chance alignment after formation. The alignment exists from the beginning. Planets do not later decide to orbit in the same direction. They emerge from material that already moves together. Their shared spin is a memory of earlier motion, preserved across immense spans of time. Observations of other systems confirm this picture. Astronomers image disks around young stars in nearby stellar nurseries. These disks show gaps where planets may be forming. Their rotation is measured, and in many cases, the direction of planetary orbits matches the disk. This agreement between theory and observation strengthens confidence in the model. You also learn that collapse does not occur all at once. Proceeds unevenly. Regions of higher density pull in material faster. Turbulence creates variations. Yet despite this complexity, the overall rotation remains coherent. The disk smooths out irregularities through countless small interactions, all governed by the same physical laws. This process explains not only direction but shape. As rotation increases, material resists collapsing directly inward. Instead, it spreads outward in a plane perpendicular to the axis of rotation. This is why disks form rather than spheres. The geometry is a consequence of motion, not an imposed design. You reflect on how quiet this transformation is. There is no sudden moment when order appears. It grows gradually, guided by gravity and constrained by conservation laws. The cloud does not need instruction. It follows physics automatically, reliably, and everywhere in the universe. By the time planets begin to assemble, the system's direction is already fixed. Changing it would require a massive external force, something large enough to overwhelm the accumulated angular momentum of the disk. Such events are rare, and their effects are noticeable when they occur. As this understanding settles in, the shared spin of planets feels less mysterious. It feels expected. The motion you observe today traces back to faint movements in cold clouds long before the sun exists, reminding you that even the smallest motions, once preserved, can shape entire systems. You rest with the idea that motion follows rules that do not tire or drift with time. Among these rules, conservation laws hold a special place. They describe quantities that remain constant as long as no outside influence interferes. One of these quantities is angular momentum, and it plays a central role in understanding why planets spin the way they do. Angular momentum is not abstract. It can be measured, calculated, and tested. In its simplest form, it depends on how fast something rotates and how far its mass lies from the axis of rotation. A slowly spinning object with mass spread far from its center can possess the same angular momentum as a rapidly spinning object whose mass lies closer in. What matters is the balance between speed and distribution. You see this principle demonstrated in controlled experiments on Earth. A rotating platform speeds up when weights are pulled inward and slows down when they are extended outward. No extra energy is added, yet the rotation rate changes. Instruments record the change precisely. The total angular momentum remains constant throughout the motion, confirming the law under repeatable conditions. This same behavior appears far beyond the laboratory. Astronomers observe stars spinning faster as they contract during formation. Neutron stars, which form from collapsing stellar cores, rotate extremely rapidly because their mass becomes concentrated into a much smaller volume. The physics is identical in form, even though the scales differ dramatically. In the context of planets, angular momentum explains why direction persists. Once a system begins rotating in a particular sense, that rotation cannot simply reverse. Reversal would require an external torque, a force applied in a way that changes the system's rotational motion. In space, such forces are rare and typically weak compared to the momentum already present. You notice how this law applies naturally to the forming solar system. The original cloud carries a small but measurable amount of rotation. As gravity draws material inward, the rotation speeds up. The total angular momentum stays the same, but its expression changes. By the time a disk forms, the direction of rotation is firmly established. Within this disk, every particle contributes. Gas molecules, dust grains, and larger clumps all share in the motion. Collisions between them redistribute energy but not overall direction. Some collisions slow local motion, others speed it up, yet the net angular momentum of the system remains unchanged. This balance is maintained automatically by physical law. You learn that conservation does not mean uniformity. Individual objects within the system can gain or lose angular momentum through interactions with each other. A forming planet may spin faster or slower depending on the details of its growth. However, these changes occur within the system, not from outside it. The overall direction stays the same. Gravitational interactions also respect conservation laws. When two bodies interact, angular momentum can transfer between them. One object may slow its spin while another speeds up. Orbits may adjust slightly, yet the total angular momentum of the interacting system remains constant. Astronomers calculate these exchanges to understand orbital evolution and spin rates. This understanding removes the need for special explanations. The shared direction of planetary spin does not require fine-tuning or coincidence. It follows directly from initial conditions combined with unchanging physical rules. Once motion begins, it carries forward through every stage of formation. You become aware that conservation laws are not optional. They are not tendencies or averages. They are strict constraints confirmed in every tested environment. From microscopic particles to galaxies, the same accounting holds. Whenever angular momentum seems to disappear, closer inspection reveals where it has gone. In planetary systems, losses do occur, but they are slow. Tidal interactions convert some rotational energy into heat. Friction within planets can alter spin rates. Even then, direction usually remains unchanged. These processes act gently over long timescales, modifying speed without overturning orientation. You reflect on how reassuring this consistency is. The universe does not invent new rules as systems grow larger or older. The same principles guide early clouds, forming stars, and mature planets. What changes is complexity, not the underlying framework. Observational evidence continues to support this view. Measurements of exoplanet systems reveal similar patterns of conserved motion. Disks rotate coherently. Planets orbit in aligned directions. Where misalignments appear, they point to later disturbances rather than failures of conservation. As you hold this understanding quietly, planetary spin feels less like a puzzle and more like a signature. It records the history of motion without needing interpretation. Direction becomes a trace left behind by physical law, still readable after billions of years. The calm persistence of angular momentum invites further reflection. If direction is preserved so reliably, then the moments when it changes must be rare and meaningful, shaped by specific events that stand out against an otherwise steady background of motion. You remain within the rotating disk that surrounds a young star, where motion is steady and direction is already set. The disk is made mostly of hydrogen and helium gas, with a smaller but crucial fraction of heavier elements in the form of dust. These dust grains are microscopic at first, composed of minerals, metals, and ices that condense from cooling gas. Their behavior is governed by simple physics, not chance. As the disk rotates, particles follow slightly different paths depending on their size and position. Gas moves smoothly, while solid grains experience gentle drag as they pass through it. This drag causes nearby particles to drift together. When they collide at low speeds, they often stick. Laboratory experiments and space-based observations confirm that under these conditions, adhesion is common rather than rare. You notice that these early collisions are frequent but not violent. The relative speeds are low because everything shares nearly the same orbital motion. This shared movement reduces destructive impacts and favors gradual growth. Over time, grains grow from microscopic specks into millimeter-sized aggregates, then into pebble-sized clumps. As size increases, gravity begins to matter. Larger bodies exert weak gravitational pulls on nearby material. This attraction slightly enhances collision rates, allowing growth to accelerate. These growing objects are called planetesimals. Their existence is inferred from both theoretical modeling and observations of debris disks around other stars. The direction of motion remains consistent throughout this process. Every collision occurs within the same rotating frame. When two objects merge, their individual angular momenta combine. Because both were already moving in the same general direction, the resulting object continues that motion. Reversal does not occur unless an impact is both large and precisely oriented, an unlikely outcome within the disk. You learn that as planetesimals grow larger, their gravity begins to shape the surrounding disk. They clear paths, draw in nearby material, and influence the motion of smaller bodies. These interactions remain local. They redistribute angular momentum within the disk but do not alter its overall direction. Computer simulations help clarify this stage. By modeling millions of particles under gravity and collision rules, scientists reproduce the formation of planets with realistic spins and orbits. These simulations begin with rotating disks and consistently end with planets that orbit and rotate in the same direction. When different outcomes appear, they are traced to specific disturbances rather than random behavior. Observations support these models. Telescopes detect gaps and rings in disks around young stars, features consistent with forming planets. The motion of gas around these gaps shows clear rotation. Everything moves together, even as structure emerges. You notice that growth is not uniform across the disk. Near the star, higher temperatures prevent certain materials from condensing. Farther out, ices can form, increasing the amount of solid material available. This difference explains why rocky planets form closer in and gas giants form farther out. Yet despite these differences, direction remains the same. As forming planets increase in mass, they begin to spin independently. This spin comes from the angular momentum of the material they collect. Accreting material arrives from slightly different angles, but because it all originates within the same disk, the net effect reinforces the existing direction. Occasionally, larger impacts occur. These collisions can alter a planet's rotation rate or tilt its axis. However, even these events usually preserve the overall sense of rotation. Complete reversals require extremely specific conditions, making them uncommon. You become aware that the disk itself slowly evolves. Gas dissipates over millions of years, blown away by stellar radiation or incorporated into planets. Solid material becomes increasingly organized into a smaller number of large bodies. Throughout this long process, conservation laws quietly govern every exchange of motion. The calm order of this environment is striking. Despite countless interactions, the system does not dissolve into randomness. The shared direction acts as a stabilizing framework. It allows complexity to grow without losing coherence. By the time planets are fully formed, their spins are not newly assigned. They are inherited. Each planet carries a rotational signature that reflects the disk from which it emerged. Differences in speed and tilt record individual histories, while shared direction records a common origin. You rest with the understanding that planets are not assembled piece by piece in isolation. They grow within a moving system that shapes them continuously. Their spin is not added at the end. It develops naturally, gradually, and predictably as matter gathers and settles. This quiet process invites a deeper question. If countless collisions occur during growth, Why does the shared direction survive so reliably, instead of being erased by random impacts, waiting to be understood through careful examination of probability and motion? You may wonder how a system filled with countless collisions can preserve such consistent direction. Collisions seem, at first glance, like events that should scramble motion. Yet when you look carefully at how these encounters occur within a rotating disk, a different picture emerges. The key lies not in eliminating randomness, but in understanding how it is constrained. Inside a rotating disk, all material shares a dominant motion around the central star. This motion sets a baseline. Individual particles may drift slightly faster or slower, or move a little above or below the disk's central plane, but these deviations are small compared to the overall flow. As a result, collisions do not occur between objects moving in opposite directions at high speed. They occur between neighbors moving nearly together. You begin to see that cancellation of spin requires very specific conditions. For two bodies to cancel each other's angular momentum, they must approach with equal mass, equal speed, and opposite rotation relative to the center. In a rotating disk, such symmetry is extremely unlikely. The geometry of the system favors alignment, not opposition. Most collisions add angular momentum rather than subtract it. When two bodies merge, their individual spins and orbital motion combine. Because both originate within the same rotating environment, their angular momenta usually point in roughly the same direction. The resulting object inherits the sum, not the difference. Statistical models make this clear. When scientists simulate thousands or millions of collisions within a disk, they find that the average outcome is not zero rotation. Instead, rotation increases gradually. Small random variations average out, while the dominant directional motion remains. Over time, this produces a clear, consistent spin. You notice that this behavior mirrors familiar physical systems. In a flowing river, individual water molecules move unpredictably, yet the river as a whole flows in one direction. Local randomness exists, but it does not override the global motion. In the disk, gravity and rotation play roles similar to the riverbanks and slope, guiding overall behavior. The disk's flat shape also matters. Because most material stays close to the central plane, collisions are more likely to occur with similar orientations. Encounters that would strongly oppose the main direction require one object to move far above or below the plane, a rare occurrence given the disk structure. Energy dissipation further stabilizes alignment. When objects collide, some kinetic energy converts into heat or deformation. This loss reduces relative motion without changing the total angular momentum of the system. Over time, velocities become more uniform, reinforcing shared rotation. You learn that larger bodies are even harder to reorient. As a growing planet accumulates mass, its angular momentum increases. Changing its spin direction would require a collision with a comparably massive object moving in a precise opposing manner. Such events are possible but uncommon. When they occur, their effects are noticeable and preserved as anomalies. Observations support this statistical understanding. Most planets rotate in the same direction with only a few exceptions. These exceptions are not scattered randomly. They often show additional signs of major disruptions, such as extreme axial tilts or unusual surface histories. Their rarity underscores how resilient alignment usually is. You also consider timescale. Planet formation takes millions of years. Over this time, countless small interactions smooth out irregularities. Short-lived disturbances fade, while persistent patterns remain. Direction, once established early, becomes increasingly difficult to overturn as the system evolves. Computer simulations reinforce this view. When initial conditions include a rotating disk, aligned outcomes dominate. When simulations remove disk rotation, planets form with random spins. This contrast highlights the importance of the shared environment rather than chance alone. You notice how this understanding reframes the role of randomness. Random motion exists, but it operates within boundaries set by conservation laws and geometry. It adds texture without destroying structure. The result is not perfect uniformity, but a strong tendency toward alignment. This balance between variability and consistency feels quietly reassuring. Nature does not need exact precision to produce order. It relies on broad conditions that guide outcomes gently but firmly. The rotating disk provides those conditions, shaping countless small events into a coherent whole. As this settles into your awareness, the persistence of shared spin feels less surprising. It feels like the natural statistical outcome of many interactions occurring under the same constraints. The few cases where alignment breaks stand out clearly, inviting careful attention to the specific events capable of leaving such lasting marks. You now notice that the solar system is not perfectly uniform. While most planets rotate in the same general direction, a small number do not. These differences are not hidden or uncertain. They are measured with the same care as all other planetary motions, and their reality is beyond dispute. What matters is not that exceptions exist, but how well they can be explained. Venus offers the clearest example. It rotates slowly and in the opposite direction from most planets. This retrograde rotation is confirmed through radar measurements that track surface features beneath its thick cloud cover. The data are precise and repeatable. Venus completes one rotation over many Earth days, and it does so in reverse compared to the typical pattern. This behavior does not appear without cause. Scientists examine several contributing factors. One involves massive impacts early in Venus's history. A sufficiently large collision can alter a planet's spin, especially if it occurs before the planet fully stabilizes. Another factor involves long-term interactions between the planet, its atmosphere, and the Sun. Over billions of years, atmospheric tides can gradually slow and even reverse rotation under certain conditions. These explanations rely on known physics, not speculation. Uranus presents a different kind of exception. It rotates in the same direction as most planets, but its axis is tilted dramatically. The planet appears to roll along its orbit rather than spin upright. This tilt is measured at over 90 degrees relative to the plane of the solar system. Spacecraft observations and gravitational modeling confirm this unusual orientation. The most widely supported explanation for Uranus involves one or more giant impacts early in its formation. A collision with a large object can tilt a planet's axis without reversing its overall rotation direction. The energy and momentum involved are immense but not unrealistic within the environment of early planet formation. Similar processes are thought to have influenced Earth's own axial tilt, though to a much lesser extent. You notice that these exceptions are few. Out of 8 major planets, only one clearly reverses its spin, and only one shows an extreme axial tilt. This rarity is significant. If spin direction were easily altered, such cases would be common. Instead, their scarcity highlights how stable rotational alignment usually is. You also learn that some moons exhibit unusual rotation. Many large moons rotate in a way that keeps the same face toward their planet, a state known as tidal locking. This behavior results from gravitational interactions over long periods. While the spin rate changes, the direction usually remains the same. Even here, conservation laws continue to apply. Mercury offers another subtle variation. Its rotation is locked in a resonance with its orbit, completing 3 rotations for every 2 trips around the Sun. This unusual ratio is measured precisely and explained through tidal forces and orbital dynamics. Yet Mercury still rotates in the common direction, showing that variation does not imply disorder. You begin to see that exceptions carry information. They act as records of past events that would otherwise be invisible. A tilted axis or reversed spin preserves the outcome of a rare interaction long after other traces have faded. In this way, planetary rotation becomes a kind of historical evidence. Observations of exoplanets support this perspective. Most systems show aligned orbits and spins consistent with formation in rotating disks. A minority show strong misalignments. In these cases, additional evidence often points to gravitational disturbances, such as close encounters with other planets or nearby stars. The same principles appear to apply beyond the solar system. You remain aware that explanations for these exceptions do not weaken the broader model. They strengthen it. A good scientific framework does not demand perfect uniformity. It predicts where variation should occur and explains why. The rotating disk model does exactly this. Careful measurement remains central. Scientists do not infer past impacts simply because they are convenient explanations. They compare models to observed spin rates, tilts, and orbital properties. When the numbers match, confidence grows. When they do not, models are revised. You reflect on how calm this process is. There is no rush to force agreement. Each planet is allowed to tell its story through motion. Most stories are similar, written in the same directional script. A few are different, written with noticeable changes, yet still following the same physical language. As this understanding settles, the solar system feels more complete rather than less orderly. Uniformity provides the rule, and deviation provides insight. Together, they reveal a system shaped by consistent laws and occasional measurable disruptions. This balance leaves you with a gentle awareness that while direction is usually preserved, time and interaction can slowly reshape motion, hinting at forces that continue to act quietly long after planets take their familiar forms. You begin to notice that rotation is not entirely immutable. Over millions or billions of years, gravitational interactions subtly modify the spins of planets and moons. The most familiar example occurs close to home, in the relationship between Earth and its moon. Tides, generated by the gravitational pull of the moon, create friction within Earth's oceans and crust. This friction dissipates energy, gradually slowing Earth's rotation. Measurements confirm that centuries ago, days were slightly shorter, and tidal data allow precise reconstruction of this long-term change. The moon itself is affected. It has rotated to match its orbital period, a phenomenon called tidal locking. Every night you observe the moon, you see the same face because its rotation period equals its orbit around Earth. This result arises naturally from the physics of gravitational torque, not coincidence. Small asymmetries in mass allow the gravitational pull to act over time, transferring rotational energy from the moon to its orbit, stabilizing its motion. Tidal interactions also operate in other planetary systems. Mercury provides a compelling example. Its 3:2 spin-orbit resonance, in which it rotates 3 times for every 2 orbits, results from the Sun's tidal effects combined with its slightly elongated orbit. Observations of Mercury's surface and orbit confirm this resonance with high precision, providing clear evidence of how gravitational forces influence spin over geologic time. Even distant exoplanets show tidal effects. Observations reveal planets orbiting close to their stars with rotation periods synchronized to their orbital periods. This is particularly common in hot Jupiters, gas giants in tight orbits where gravitational forces are intense. Spectroscopic measurements of these exoplanets' atmospheres allow astronomers to infer rotational velocities, showing that tidal locking is widespread across the galaxy. You notice that while these processes modify rotation rates, they rarely change the fundamental direction of spin. Angular momentum is still conserved. A planet may slow, speed up slightly, or experience shifts in tilt, but reversing its overall rotation is exceedingly rare. The system retains a memory of its original orientation, even as time acts on it slowly and relentlessly. Friction within a planet also contributes. Viscous flows in molten cores, interactions between mantle and crust, and atmospheric drag all redistribute energy. These processes operate over millions of years and are measurable. Seismic data, geodetic studies, and satellite tracking allow scientists to quantify the effects, confirming that internal physics modifies rotation gently, without disrupting directional alignment. You see that orbital resonances amplify these effects in predictable ways. When 2 bodies exert repeated gravitational influences on each other at regular intervals, their spins and orbits gradually adjust. Jupiter's moons, Io, Europa, and Ganymede, form a resonance chain. Their rotations and orbital periods lock in precise ratios. Observations of orbital periods and surface activity provide evidence of energy transfer between rotation, orbit, and internal heating. The solar system's long-term stability is remarkable. Computer models simulate billions of years of evolution, including tidal interactions, planetary encounters, and frictional forces. These models reproduce current spin directions and orbital arrangements. Deviations exist, but they are limited and can be traced to specific perturbations. The overall picture confirms that rotational alignment is resilient over cosmic timescales. Even Earth's axis shifts slowly due to precession and nutation, subtle changes influenced by the gravitational pull of the Moon and Sunday. These shifts, measurable with modern instruments, do not reverse rotation but slightly reorient the spin axis over tens of thousands of years. Paleoclimate studies and precise astronomical measurements show that these motions are slow, predictable, and consistent with physical laws. You notice that the Moon-Earth system is a powerful example of long-term change. Fossil evidence, tidal rhythmites, and astronomical models allow scientists to reconstruct the history of day length and orbital distance. Over billions of years, Earth's rotation slows by about a few milliseconds per century, and the Moon drifts gradually outward. The process is ongoing, measured precisely, and explained by physics alone. Exoplanet observations offer additional insight. Planets close to their stars often reach equilibrium states where tidal forces prevent further rotational change. Systems with multiple planets interacting gravitationally show slight variations in spin rates and orbital tilts. These small differences reinforce the idea that rotation is influenced continuously but direction remains strongly constrained. The physics behind all of this is straightforward yet profound. Torque from gravitational forces acts over time, redistributing angular momentum within the system. Friction converts rotational energy into heat. Resonances amplify or stabilize effects. Yet no new principle is required. The same conservation laws you have seen in earlier examples apply consistently, producing measurable, long-term changes without breaking the fundamental pattern. You begin to appreciate the subtlety of time in planetary motion. Rotation is not frozen, but it evolves gradually, like a slow pulse felt over eons. Each planet's spin records both its origin and its history, reflecting ancient formation processes as well as ongoing interactions with neighboring bodies. Observational evidence, from satellites, telescopes, and geological records, confirms that these processes are both predictable and continuous. This awareness leaves you with a quiet sense of balance. Even as tides, friction, and resonances slowly modify rotation, the original direction persists. Shared spin is resilient, not because it is rigid, but because the laws governing motion act steadily and consistently. Time is an agent of change, yet one that preserves the deep order established billions of years ago. As you consider the subtle forces at work, you sense that the behavior of distant planets may reveal similar patterns. Measuring spin across the galaxy allows you to see how common these interactions are and how universal the preservation of direction truly is. The story of motion continues, extending quietly from your solar system to the vast expanse of observed exoplanets. You now turn your attention outward, to planets orbiting stars far beyond your sun. These exoplanets are detected through precise techniques that allow scientists to measure their orbits, sizes, and in some cases, rotational behavior. Two primary methods provide much of this information. The first is transit photometry, in which a planet passes in front of its star from our perspective, causing a tiny, periodic dip in brightness. The second is spectroscopy, which detects shifts in the star's light caused by the planet's motion or the planet's own rotation. The data reveal remarkable regularities. Many exoplanets orbit their stars in planes that are aligned with the remnants of the disks in which they formed. These systems echo the flat, rotating structure observed in your own solar system. Observations with space-based telescopes such as Kepler, TESS, and Cheops capture thousands of planets across a range of star types. When the orbital inclinations of these planets are measured relative to the equatorial planes of their stars, a strong preference for alignment appears. You notice that misaligned or retrograde orbits exist, but they are relatively rare. These outliers are often associated with specific histories, such as gravitational encounters with other planets, close stellar flybys, or long-term dynamical evolution. Their rarity underscores the principle that the rotation of disks naturally produces aligned orbits and spins, reinforcing what you have learned from your solar system. Spectroscopic techniques allow direct measurement of spin in certain exoplanets. When a planet rotates, the light from its approaching limb is slightly blue-shifted, while the receding limb is red-shifted. High-resolution spectroscopy can detect this subtle effect, revealing the rotational velocity of the planet. Combining these measurements with orbital information provides a view of both speed and direction of rotation. Hot Jupiters offer a particularly clear example. These gas giants orbit very close to their stars, sometimes completing a revolution in only a few days. Many of them are tidally locked, so one face always points toward the star. Observations confirm this synchronization, and the few that are misaligned often reveal the presence of additional gravitational interactions in the system. These measurements demonstrate that even in extreme conditions, rotational behavior is consistent with physical expectations. You learn that multi-planet systems frequently show coherent spin directions. Kepler 90, for example, contains 8 planets orbiting a single star. Detailed analysis of orbital inclinations and spacing indicates that the planets move within a narrow range of alignment, similar to the solar system. The precision of these measurements confirms that alignment is not coincidental but a natural outcome of formation in a rotating disk. You also notice that stellar rotation correlates with planetary motion. Young stars typically spin rapidly, surrounded by disks of gas and dust that inherit this rotation. Planets that form within these disks carry the same sense of motion. Measurements of spin-orbit angles, obtained through spectroscopic observations of the Rossiter-McLaughlin effect during transits, show that the majority of systems have spins roughly aligned with their parent stars. Misalignments provide clues about past interactions rather than initial formation. These observations highlight a remarkable universality. Across the galaxy, the same physical processes appear to govern the formation of planetary systems. Rotating disks create flattened, coherent structures. Conservation of angular momentum preserves direction. Collisions and growth occur within these constraints, producing a predictable pattern of spin alignment. You reflect on the significance of this evidence. Exoplanets provide an independent confirmation of principles derived from studying your own solar system. What was once observed locally is now seen on a cosmic scale. Thousands of systems reveal the same pattern, demonstrating that shared rotational direction is not unique or coincidental, but arises naturally from known physics. The data also allow comparison of different planetary types. Rocky planets, gas giants, and even sub-Neptune-sized bodies show similar trends in spin orientation relative to their star. While absolute rotation rates vary due to mass, formation history, and tidal interactions, the underlying alignment remains a common feature. This consistency across planet types strengthens the argument that shared direction is an intrinsic property of disk-based formation. You notice that measurement techniques continue to improve. Future telescopes, such as the James Webb Space Telescope and ground-based extremely large telescopes, will provide more precise determinations of spin rates, inclinations, and even axial tilts. These data will refine the understanding of how universal these patterns are and may reveal subtle variations caused by previously undetectable interactions. You also become aware of the limits of observation. Not every planet's spin is measurable, and some data are incomplete or noisy. Yet even with these limitations, the patterns are clear. Statistical analyses show that alignment is strongly favored, with deviations mostly explained by identifiable processes. The principles of disk formation, angular momentum conservation, and growth within a rotating environment consistently predict what is observed. As you absorb this perspective, the connection between your solar system and distant planetary systems becomes tangible. The same laws of physics operate everywhere, producing ordered motion that survives billions of years. Exoplanets do not simply orbit randomly. They carry the imprint of the disks in which they formed. Their spins are records of both origin and history, visible across light years. You end with a quiet recognition of continuity. Local observations, solar system dynamics, and exoplanet studies all converge on a single conclusion. Shared spin is expected and pervasive. These findings deepen your appreciation for the universality of physical laws. From nearby planets to distant systems, rotation preserves memory, alignment, and coherence, revealing a cosmos governed by consistent and observable principles. You now widen your perspective, moving beyond planets to consider stars and galaxies. The same physical principles that guide planetary spin also govern these larger systems. Angular momentum remains central, dictating how matter behaves during collapse and formation. Observations across the universe reveal that stars rotate and galaxies spin, both following predictable patterns that emerge from initial conditions and conserved motion. Stars themselves inherit rotation from the clouds of gas in which they form. Molecular clouds collapse under gravity, just as in planet formation, and any small initial spin is amplified as contraction continues. Measurements of young stellar objects show a broad range of rotation rates, with some stars spinning rapidly, others more slowly. These rates are consistent with angular momentum conservation and the distribution of mass within the collapsing cloud. Spectroscopy allows astronomers to measure stellar rotation directly. Light from the approaching limb of a star is slightly blue-shifted, while light from the receding limb is red-shifted. The resulting spectral line broadening provides a precise measurement of rotational velocity. Observations confirm that most stars rotate in the same direction as the local angular momentum of their birth cloud, demonstrating a continuity between molecular clouds, forming stars, and eventually any orbiting planets. Galaxies, on an even larger scale, display similar behavior. Spiral galaxies exhibit rotation around a central axis, with stars and gas orbiting the galactic center. Observations using radio telescopes to measure neutral hydrogen, as well as optical spectroscopy of stars, reveal detailed rotation curves. These curves show how velocity changes with distance from the center, confirming that angular momentum plays a fundamental role in shaping galactic structure. The formation of galaxies begins with enormous clouds of gas and dark matter. As these clouds collapse under gravity, rotation prevents complete radial infall. The same principle that flattens planetary disks applies here on a grander scale. Conservation of angular momentum ensures that material spreads into a flattened, rotating structure rather than collapsing into a single point, producing the familiar spiral or disk shapes observed in countless galaxies. You notice that, just as in planetary systems, collisions and interactions can alter spin. Galaxies merge, tidal forces distort orbits, and accretion events redistribute angular momentum. Yet the overall rotational pattern persists. Even after complex interactions, stars and gas often maintain a coherent spin relative to the larger system. Observational surveys confirm that, statistically, rotation remains aligned with the initial angular momentum of the progenitor clouds. Differentiating scales becomes important. Planetary spin is a local phenomenon, influenced by the immediate disk and interactions with nearby bodies. Galactic rotation involves billions of stars, vast clouds of gas, and the gravitational influence of dark matter. Yet both systems obey the same laws. Angular momentum is conserved, motion is constrained by geometry, and formation processes produce coherent rotation from initial asymmetries. You see that the same observational techniques provide insight across scales. Doppler measurements reveal stellar spin, gas velocity, and galactic rotation. High-resolution imaging shows disk structures around stars and spiral arms in galaxies. The alignment of angular momentum at each level indicates that the underlying physics operates universally, from microscopic interactions of dust grains to the movement of billions of stars. Statistical analysis across galaxies reinforces these conclusions. Surveys of hundreds of spiral galaxies demonstrate consistent rotational behavior, with velocity profiles matching theoretical predictions. When galaxies interact, tidal tails and warps may form, yet even in these cases, angular momentum is redistributed rather than destroyed. The universe preserves motion across vast scales in a manner fully consistent with conservation laws. The connection between planetary systems and galaxies becomes clearer when you consider hierarchical formation. Molecular clouds form within galactic disks. Stars form within those clouds, inheriting local rotation. Planets form around those stars, inheriting disk-aligned motion. Each level carries a record of angular momentum from the level above, preserving directionality across space and time. Observations of exoplanets, stars, and galaxies confirm that this hierarchical pattern is not theoretical. It is visible in the universe. You notice that scale does not alter the qualitative outcome. Collisions, mergers, and gravitational disturbances modify velocities and spin rates, but the fundamental direction imposed by initial rotation persists. Both in planetary disks and galactic disks, conservation laws ensure that angular momentum cannot vanish spontaneously. The resulting structure and motion reflect the cumulative history of interactions under these constraints. Even when observing galaxy clusters, rotation is evident though less coherent. Individual galaxies may orbit cluster centers, and interactions redistribute angular momentum over time. Yet within each galaxy, rotation remains ordered. The universe, it seems, maintains a hierarchy of coherent motion at each scale, demonstrating the pervasive influence of the same physical principles you observed in forming planets. You begin to appreciate continuity across scales. The slow, steady spin of a dust grain in a protoplanetary disk and the sweeping rotation of an entire spiral galaxy are governed by the same principles. Angular momentum acts as a unifying thread, connecting seemingly disparate systems through consistent, observable laws. Each level of structure preserves a memory of its formation environment, providing evidence that motion is both stable and predictable. Observational confirmation extends to star clusters as well. Young clusters often show alignment of rotational axes among constituent stars, reflecting their common origin in a collapsing molecular cloud. These correlations diminish over time as dynamical interactions increase, yet the initial alignment reinforces the role of conservation laws in shaping structure from the very beginning. You notice that at every scale, rotation is a record of history. Planetary spins, stellar rotation, and galactic motion all encode the dynamics of formation. Disruptions leave identifiable marks, whether through tilted axes, retrograde motion, or orbital misalignment. By measuring these quantities, astronomers reconstruct past events and gain insight into the processes that generated the cosmos observed today. The persistence of directional motion across planets, stars, and galaxies deepens your sense of order in the universe. The same laws that govern a slowly spinning protoplanetary disk continue to operate in the immense scale of galactic disks, illustrating continuity across vast distances and timescales. Physical law ensures coherence, even as complexity increases. You rest with the awareness that motion is both a record and a force. Each rotating system tells a story of origin, growth, and interaction, bound together by the unchanging principle of angular momentum. Across billions of light-years, from dust grains to galaxies, the universe exhibits a calm consistency, revealing the shared language of physics that governs everything in motion. You now notice that rotation has effects beyond simple movement. It shapes the environment in which life can exist. The duration of a planet's day, determined by its spin rate, sets the rhythm of temperature fluctuations between daylight and night. On Earth, a roughly 24-hour rotation ensures that temperatures change gradually rather than abruptly, providing a stable climate that allows ecosystems to develop and adapt. Without this predictable cycle, extreme variations could prevent complex life from persisting. Rotation also influences the behavior of planetary atmospheres. The Coriolis effect, caused by a planet spinning on its axis, directs winds and currents. On Earth, this effect organizes large-scale weather patterns, including trade winds and jet streams. Models of atmospheric circulation confirm that without spin, heat distribution from equator to poles would be less efficient, leading to larger temperature extremes and less hospitable conditions. Observations of other planets and their atmospheres demonstrate similar connections between rotation and weather dynamics. Magnetic fields are another consequence of planetary spin. On planets with molten, conducting cores, rotation helps sustain a dynamo effect. The movement of liquid metal generates electric currents, which in turn produce magnetic fields. Earth's field protects the surface from harmful cosmic and solar radiation. Without rotation, a planet could lose its magnetosphere, and with it, the shielding necessary for maintaining an atmosphere conducive to life. Measurements from spacecraft and magnetometers confirm the link between spin, core dynamics, and magnetic field strength. Axial tilt, or obliquity, interacts with rotation to produce seasonal variation. On Earth, a tilt of about 23.5 degrees combined with daily rotation results in gradual, predictable seasons. These variations allow ecosystems to adapt over time. Planets with unstable spin or extreme tilts may experience erratic climate changes, making sustained habitability more difficult. Computer simulations of exoplanets illustrate how spin and tilt together influence temperature distribution, ice coverage, and potential liquid water. You observe that rotation also affects geophysical activity. A spinning planet's angular momentum contributes to the distribution of internal stresses. Mantle convection, plate tectonics, and volcanism are influenced by the balance of rotational and gravitational forces. These processes recycle nutrients, shape landscapes, and contribute to atmospheric composition, indirectly supporting life. Seismic studies and geological models confirm that the interplay between rotation and internal dynamics is measurable and predictable. Tidal forces play a complementary role. The gravitational interaction between a planet and its moon, or between a planet and its star in close orbits, can modify rotation over time. Tidal friction gradually slows spin, affects axial tilt, and influences orbital resonance. Earth's moon has stabilized the planet's rotation, maintaining a relatively constant tilt over geological timescales. Paleoclimate records show that this stability has allowed consistent seasonal cycles for hundreds of millions of years. Observations of other planets support these principles. Venus rotates slowly and in the opposite direction of most planets, resulting in extreme surface temperatures and atmospheric dynamics that differ markedly from Earth. Mars, with a rotation similar to Earth's but a weaker magnetic field, illustrates how rotation alone does not guarantee habitability, yet it contributes to environmental conditions. Comparing planets within and beyond the solar system highlights the interconnected role of rotation, tilt, atmosphere, and magnetic shielding. You notice that rotation also interacts with orbital characteristics. Day length relative to orbital period affects climate and potential habitability zones. For instance, tidally locked exoplanets present one hemisphere permanently to their star, producing extreme temperature gradients. Models of such planets show that a slow or synchronized spin dramatically changes atmospheric circulation and heat redistribution. These cases underscore how spin rate and direction influence long-term environmental stability. The study of spin and habitability is not purely theoretical. Direct measurement of exoplanet rotation is increasingly possible. Techniques such as Doppler spectroscopy detect rotational broadening in planetary atmospheres, revealing rotation rates and, in some cases, axial tilt. Combined with transit photometry and orbital modeling, these measurements allow scientists to infer climate regimes and assess potential for life-friendly conditions. Observations consistently support the conclusion that rotation is a critical factor in shaping planetary environments. You reflect on the interplay of spin and habitability as an intricate balance. Rotation establishes cycles, drives magnetic fields, organizes atmosphere, and influences geology. All these effects interact continuously, producing conditions that are stable enough for life to develop over millions of years. Even small changes in rotation can have significant long-term consequences, illustrating the importance of conserved angular momentum in sustaining habitability. Studying Earth in this context provides a benchmark. Measurements of rotation rate, axial tilt, magnetic field strength, and ocean currents offer a comprehensive picture of how spin influences the biosphere. Climate models validate that these factors work together to maintain temperature ranges suitable for life. Observational data from satellites and ground stations confirm both current conditions and long-term trends influenced by rotation and tidal interactions. You see that rotation is more than movement, it is a stabilizing force. While gravitational interactions, tidal friction, and internal dynamics can slowly modify spin, the general direction and rhythm remain largely constant. This constancy allows environmental cycles to persist over geological timescales, providing a foundation for stable climates, weather patterns, and magnetic protection. Comparative studies of exoplanets and moons provide additional evidence. Observed planets in habitable zones with measured rotation rates often show conditions that could allow liquid water, moderate temperatures, and protective atmospheres. These correlations reinforce the principle that stable, directional spin is a key factor in creating life-supporting environments. You notice that even small planets or moons with minimal spin can experience tidal heating or rotational irregularities, but extreme deviations are rare. When rotation deviates substantially from the expected pattern, environmental conditions tend to be less favorable. The consistency of spin direction in most planetary systems, therefore, is not only a matter of formation mechanics but also a factor that indirectly supports conditions suitable for life. As you absorb this understanding, you appreciate that rotation operates quietly yet profoundly. Its influence pervades climate, atmosphere, and geology. The direction and rate of spin are not trivial. They provide a stable backdrop for the emergence and persistence of life. Each planet's rotation is a record of both formation and ongoing dynamical processes, maintaining the rhythm that supports habitability. You end with a gentle awareness that spin is a bridge between cosmic physics and environmental conditions. By preserving direction and modulating speed, rotation establishes the temporal and magnetic structure necessary for life. The same physical principles that shaped planets billions of years ago continue to act, quietly maintaining the patterns that make stable climates and magnetic protection possible. You step back and observe the entirety of what has unfolded across billions of years and countless kilometers of space. From tiny dust grains in a rotating disk around a young star to fully formed planets orbiting consistently in a shared direction, the evidence points to a simple but profound conclusion. The universe preserves order naturally. Angular momentum, conservation laws, and the geometry of rotating disks govern motion in ways that produce predictable and measurable outcomes. Every planet you have considered carries a record of this order. Their spins and orbits are not random. They are the logical consequence of growth within a rotating environment. Microscopic collisions, adhesion of dust grains, accumulation of planetesimals, and the gentle tug of gravity all combine to produce alignment. Statistical principles demonstrate that even millions of interactions do not erase the overall direction, because the system is constrained by conserved momentum and disk geometry. You notice that the exceptions, though intriguing, strengthen the overall understanding. Retrograde rotations, extreme axial tilts, and tidal locking events are rare and can be traced to identifiable physical processes. Collisions, resonance, and gravitational perturbations explain these anomalies without requiring extraordinary assumptions. They serve as a reminder that while local variability exists, the underlying rules governing motion are robust and universal. Looking beyond the solar system, exoplanets reinforce this perspective. Thousands of observed planetary systems display alignment between orbital planes and rotational direction, consistent with formation in rotating disks. Even when misalignment occurs, detailed study often reveals past interactions or tidal influences as the cause. The coherence of spin direction across systems demonstrates that these principles extend beyond your local neighborhood, observable on a galactic scale. Stars, too, exhibit this calm order. Young stellar objects rotate in alignment with the angular momentum of their progenitor clouds, and their spin rates follow predictable ranges determined by mass, contraction, and magnetic braking. Observations across stellar populations confirm these trends. Galaxies, composed of billions of stars, also spin in a structured and measurable way, with rotation curves that match theoretical predictions derived from conservation laws and the distribution of visible and dark matter. You perceive that across scales, from dust grains to planetary systems, stars and galaxies, rotation acts as both a record and an organizing principle. Motion preserves history while creating structure. Conservation of angular momentum ensures that once direction is established, it remains a persistent feature unless acted upon by an external, significant force. This principle explains the remarkable consistency you have observed. Internal processes also contribute to stability. Tidal interactions, friction, and resonance may alter rotational speed or tilt over long periods, but these processes do not destroy directional coherence. They fine-tune planetary and stellar behavior, producing predictable outcomes rather than chaos. The slow, continuous influence of time shapes rotation without violating the fundamental rules, illustrating that order is maintained even in dynamic systems. You notice that rotation directly impacts planetary environments. Spin rate and axial tilt influence climate, atmospheric circulation, and magnetic field generation. Stable rotation underlies day-night cycles, weather patterns, and conditions that can support life. Habitability is therefore intertwined with the same physical principles that establish spin, linking fundamental mechanics to the long-term stability of planetary systems. The study of exoplanets and distant galaxies reveals that these processes are not isolated. They operate everywhere under the same physical laws. Observation confirms that rotation, alignment, and angular momentum are pervasive properties of the cosmos. The universe consistently produces structured motion across scales, demonstrating that complex order emerges naturally from simple, well-understood principles. You reflect on the mathematical elegance underlying these observations. Conservation of angular momentum, Newtonian mechanics, and gravitational dynamics provide precise predictions for how material will behave in rotating systems. Simulations, computer models, and analytical calculations reproduce observed planetary spins, orbital inclinations, and galactic rotations. These results are not arbitrary. They are measurable, repeatable, and verifiable. Looking at the full picture, you see the gentle interplay of processes that leads to coherence. Early disk rotation establishes a baseline. Particle collisions, accretion, and planetary growth preserve alignment. Gravitational interactions, tidal effects, and minor collisions introduce variability, but the dominant pattern persists. Across the galaxy, across billions of years, direction survives as a reliable feature of motion. Even anomalies tell a story. Retrograde spins, tilted axes, and tidal locking provide insight into rare events that punctuate otherwise consistent evolution. These cases are instructive, showing how systems respond to extraordinary interactions while still adhering to fundamental physics. They remind you that while nature allows variability, the overall framework of order remains intact. You notice that this calm order is both predictable and flexible. Planetary systems can evolve, stars can slow their rotation, and galaxies can merge. Yet the laws governing motion produce outcomes that remain consistent with the principles you have observed. The universe does not need perfect precision to maintain order. Boundaries imposed by angular momentum, gravity, and disk structure ensure that coherent rotation is the expected result of natural processes. You see that motion serves as a thread connecting scales and systems. Dust grains record the spin of their disk. Planets inherit that rotation. Stars reflect the angular momentum of their clouds. Galaxies maintain coherent rotation through the interactions of billions of stars and vast clouds of gas. At every level, rotation preserves a memory of formation, demonstrating continuity from the smallest to the largest structures. Quietly, you realize that the universe balances stability and change. Rotational direction is robust, yet spins are never perfectly uniform. Small variations provide insight into past interactions, tidal evolution, and the cumulative influence of time. These details enrich your understanding, allowing a deeper appreciation for the processes that shape motion throughout the cosmos. In this expansive view, order emerges not through design or chance, but through the consistent application of physical law. Conservation of angular momentum, coupled with the dynamics of formation and interaction, naturally produces aligned rotation across planets, stars, and galaxies. The pervasive coherence observed across space and time underscores the predictive power of fundamental physics. As you settle into this realization, you feel a gentle sense of completeness. The evidence, models, and observations converge on a single, calm conclusion. Shared rotational direction is an expected, natural outcome of formation within rotating systems. It is neither mysterious nor arbitrary. Instead, it reflects the quiet, steady principles that govern motion in a dynamic universe. You end with a soft awareness that this coherence connects the smallest scales of planetary disks to the largest structures in the universe. Rotation preserves memory, maintains structure, and records the history of formation. Even as the cosmos continues to evolve, the same laws of motion ensure that order quietly persists, inviting ongoing curiosity and reflection on the processes that shape everything in motion.